Hello everyone, my name is Radhika and today I will be explaining the most important concept in machine learning and deep learning, gradient descent algorithm. The main purpose of this algorithm is to minimize the errors during the training time. So let's have a look. So in machine learning we train many models and for that model we calculate the error, the loss function, and you can take example like in linear regression we use mean squared error. In classification problem we use cross entropy. So these error functions varies according to the algorithm, according to the model. So why gradient descent? It is an iterative optimization algorithm that helps us to reach the minimum point step by step. So this idea is inspired by the slope downhill. So what is this slope downhill? The rolling ball down a hill. So imagine you place a ball on a hill. Gravity will make the ball roll downhill. The ball will always move in the direction of the steepest slope and it will be downward. So finally it settles at the lowest point of reaching the minimum error in machine learning. So that's the concept, that's the general concept, and then we used it in our model training in a mathematical way. So let's dive deeper into it. So let's look towards the definition. Gradient descent is an optimization algorithm used in machine learning and deep learning to minimize the error by updating the model's parameters step by step. The step by step word is very important because we are going step by step, like after one point after another. We are going in a sequence. It's like sequence. So our main purpose is to find the lowest point of a curve by taking small step downhill in the direction of the slope. So we can imagine like we have to go step by step. We cannot jump from one step to another step. We have to step one, step two, step three. We have to take all the steps. So here is a mathematical intuition of that problem, that how we calculate, how we adjust these weights. Like in new deep learning, when we do the back propagation, what we do? We adjust the weight, and by adjusting that weight, we get minimum error. So theta new is equal to theta old minus eta into derivative of j with respect to theta. So what is theta? Theta is a weight parameter. So we have to adjust that parameter only. So we take old parameter and minus learning rate. Learning rate means what is it? It's a step size, that on in what step you have to go, in what step you have to jump, and the gradient is a slope of error. So the error will be the one point, like you have to calculate root mean square for one point, and that point you are going to plot on the graph, and that point slope is our gradient. So let's take the example and understand how it works. So here we took one error function, means loss function, and this is the function. Now how we are going to calculate? We have already given that w is equal to 4 is minimum. At that point we are going to have minimum error. So we just start with 0 and gradually we come to the 4, and our rate is 0.1. So first we what we will do, we calculate the derivative. So we here we calculate the derivative 2 into w minus 4, and in each iteration first we will take w is equal to 0, then our gradient will become minus it. How it come? Because here in derivative we put w is equal to 0, and 0 minus 4 is equal to minus 4, 2 into minus 4 is equal to minus it. So update the weight by weight formula, w is equal to old weight minus learning rate into minus 8. So here you can see how it happens, and our updated weight is 0.8. Then again we take that weight, again we apply that gradient, again we get updated weight as 1.44. Again we take 1.44 as updated weight, again we calculate, again we update the weight. We are going to do it till we get approximately w is equal to 4. So it can be any step, like we can get it on 10 step, 12 step, we don't know. So this is the mathematical intuition. Now we will understand the base, that where this algorithm came. So here, so the root concept is calculus, that we are taking the derivative. So gradient descent is built on idea of derivatives in calculus. The derivative tells us the rate of change of a function. So in what rate the function is changing, and in on what range it's going downwards, it's coming to the global minima. If the slope is positive, function increases. So if the slope is positive, then the function is going to increase, and we have to minimize the error. So we are going to move opposite direction, means we have to move to the left. If the slope is negative, then function is going to decrease now. So to minimize this, we have to move to the right. So here is, we can understand it by simplifying. Minimizing a function is equal to moving it in the opposite direction of the gradient. So here is the first is calculus. Then second one is Taylor expansion. Taylor series. You often heard about the Taylor series in your linear algebra classes. So there we have this formula of updating weights, and we are using that the same formula for our gradient descent for our updated weights. Here you can see how it goes, and here in this figure you can have the understanding of the steps. That first steps is calculating loss, second step is determining the direction to move the weights and biases. So if I have already said that if slope is positive, function increases, move left. If slope is negative, then move to right. Then move a small amount in the direction that reduces error is the third step, and fourth is repeat the process until loss can't be reduced. So we are going to repeat all these steps until our loss is going to be zero. So these are the types of the gradients, because we cannot use one type of gradient for all the problems, because here you can see the batch gradient descent. When we use it, when the entire dataset is small, it's suitable for small dataset, and we use the entire dataset to compute the gradient in each step. Second one is stochastic gradient descent. Here updates parameters for one random sample at a time. So we are not going to take all the dataset, we are going to take random samples and then calculate its gradient. So it's fast, helps to escape local minima. Third one is mini batch gradient descent, splits data into small batches, updates parameters using each batch. So here we can split the data, because in large data sets you cannot calculate the gradient for all. We have to split that into batches and then calculate for them, and it's efficient for GPUs. So here you can see the diagrams how these functions operate independently and differently. So there are some challenges in gradient descent. So first challenge is, if the learning rate is too high, we may overshoot the minimum. In this figure, look at this third diagram, that learning rate is too high. So when the learning rate is too high, you can see that how the function is jumping from one to other point, other to other, and this happens repeatedly, and you cannot going to reach that local minima. If learning rate is too small, training becomes slow. So here you can see the training, in the training part, the function is trying to cover all the points, and all the points are important, but not that. In large datasets, it's going to crash your code, it's going to slow down your training time. So we need to choose optimal learning rate for that. So there is third drawback also, it can get stuck in local minima instead of the global minimum. We need the global minimum, and it is at this point. This is our global minimum. For very large data sets, computing gradient for all samples is costly. So I have said it already, we need some other gradients also, like stochastic mini batch for larger data sets for fast execution. There, there is one more problem, like vanishing gradient. In deep neural networks, during backpropagation, gradients becomes very small in earlier layers. This makes weight updates negligible. Network stops learning. So it's the problem that at some point the gradient starts becoming near to zero. So there is no weight update, and if the weight update is there, it will be like 0.001 and like this, and it's not going to change the training process of that model. It's going to worsen that process. So why this happens? It happens with some functions like sigmoid, tanh. Derivatives of these functions are very small when inputs are large. Repeated multiplication deep layer string gradient, and they vanish out. The gradient becomes with no remains with no value. So there are solutions like we can use ReLU activation function, we can use batch normalization, we can use better optimization. So this is the vanishing gradient. So what we learned that how gradient descent optimization algorithm works. Its types like batch gradient, stochastic gradient, this mini batch gradient, its application where it used like in machine learning, deep learning algorithms, linear regression, logistic regression, neural networks, and what are the challenges, like if the learning rate is too high, it becomes very difficult to uh, catch the global minimum. It overshoots like local minima or plateaus can trap the model. So if we cannot go reach the global minimum, so the error will stuck at the local minima. And vanishing gradients in deep networks. So in deep networks, what happens? Vanishing gradients happen. So this was all. Thank you.